Hey there, and welcome back to our channel. If you're passionate about artificial intelligence, machine learning, or just curious about how computers learn from data, you're in the right place. Today, we're diving into the fascinating world of contrastive learning. So, grab a snack, get comfy, and let's explore this exciting topic together. Now, you might be wondering, what exactly is contrastive learning, and how does it work? Great question. To answer that, let's first break down the concept and see why it's becoming such a pivotal technique in the realm of machine learning. Contrastive learning is a type of self-supervised learning that focuses on training models to differentiate between similar and dissimilar data points. Essentially, it teaches the model what makes two pieces of data similar or different, which is crucial for a variety of tasks in AI, such as image recognition, natural language processing, and even recommendation systems. Let's utilize a simple example. Imagine we have a dataset filled with images of cats and dogs. In a traditional supervised learning approach, you would label each image as either cat or dog. However, in contrastive learning, we focus on the relationships between the images themselves. We create pairs of images, some of which are similar and some that are dissimilar. The model learns to pull together the representations of similar pairs while pushing apart the representations of dissimilar pairs in a learned feature space. This process is often facilitated by a method called contrastive loss, which measures how well the model is doing in distinguishing between similar and dissimilar pairs. To illustrate this further, let's talk about a popular contrastive learning algorithm called SimCLR. Developed by Google Research, SimCLR employs a technique called data augmentation. It creates different augmented versions of the same image, like changing brightness, cropping, or applying filters, so that the model learns to recognize that these variations still represent the same underlying object. Research has shown that models trained with contrastive learning can achieve state-of-the-art results in various benchmarks. For instance, in image classification tasks, SimCLR outperformed traditional methods by leveraging the rich information present in unlabeled datasets. In fact, it was reported that SimCLR achieved accuracy rates comparable to supervised learning models, despite being trained on a fraction of the labeled data. But why is contrastive learning so powerful? The key lies in its ability to learn meaningful representations without the need for extensive labeled datasets. This is particularly useful in real-world scenarios where labeled data is scarce or expensive to obtain. By utilizing large amounts of unlabeled data, contrastive learning opens up new avenues for training robust models. Contrastive learning isn't just limited to images, either. It's also making waves in natural language processing. For example, models like SentenceBERT use contrastive learning to generate sentence embeddings. By training on pairs of similar and dissimilar sentences, these models can better understand semantic similarities, leading to improved performance in tasks like question answering, paraphrase detection, and even sentiment analysis. Moreover, contrastive learning has found applications in recommendation systems, where it helps in understanding user preferences by contrasting items users have interacted with versus those they haven't. This allows for more accurate recommendations tailored to individual tastes. However, it's worth noting that contrastive learning is not without its challenges. Selecting the right pairs of similar and dissimilar data can be tricky, and the quality of the learned representations heavily depends on the data quality. Additionally, as the datasets grow larger, computational costs can increase significantly, requiring advanced techniques to manage resources effectively. To wrap it up, contrastive learning is a powerful self-supervised learning technique that allows models to learn robust representations from unlabeled data by focusing on the relationships between data points. Its applications span across various domains, including image recognition, natural language processing, and recommendation systems, making it a game-changer in the AI landscape. If you found this video helpful and want to learn more about cutting-edge AI techniques, don't forget to hit that like button and subscribe to our channel. And if you have any questions or topics you'd like us to cover next, drop them in the comments below. Thanks for watching, and until next time, keep exploring the exciting world of technology.